Okay, we're going to go ahead and get started. This is the very fun part of the show. We're going to actually have our technical demonstration of the module. And to lead us through that, I'm incredibly excited. You've already heard about Carbon Capture's CTO and visionary designer, Saeb Besarati, is going to go ahead and start this program.
Yeah, so happy to be here. Thank you very much, everyone, for joining us today for this special day for Carbon Capture team. It's really remarkable to see this is coming to life. Before starting going to the demonstration, I just want to take a moment, really appreciate the hard work of the CCI team. Like I am a small part of the team that presenting like 65 people. A lot of people worked long hours, and there was a lot of support from their families to put this long hours into this project. I just want to appreciate that, and I think this wasn't possible without the support, like a really extended group of teams. So I really appreciate that. So today for our demonstration, I'm going to basically get help from two of my colleagues, and I'm going to introduce them because sometimes we are going to hand off the microphone. Without this, more interactive, so instead of like me only speaking here. So we have Brian Holman, manager of our systems engineering, and we have Duran. He's our plant operator. So Duran is responsible for working with HMI and basically doing the control of the plant. Brian is going to work with him, and whenever there is interesting part of the data coming in, he's going to basically take over the mic and walk you through what's going on. I will be mostly responding to the questions that Chris has. And yeah, I think before we start the module operation, I just wanted to put two slides as an intro, because I want to basically tell you what you expect to see before showing a bunch of data and graphs here. I think you already know this is we call it phase 0 because this is just a stepping stone. This is the beginning for us in a long journey, but it is our commercial scale module. It has 12 reactors, and the way it's been architectured, the 12 reactors works in 3 independent sets. So we have each set is a 4 reactor each. So what we are going to do, we are going to operate at this point. We are going to only do the absorption on one reactor set and desorption on other reactor set. What happens in the real life is basically there is a synchronization in our control to make sure we are utilizing our balance of plant efficiently. So we are moving steam and we are moving our energy between different parts of the module at the time. So that's why it has 3 reactor sets, and each reactor set has 4 reactors in it. So the capacity today is 500 tons of carbon dioxide removal per year. As you have heard, we are working on upgrading our sorbents. We have active teams and programs in place to make sure always we are replacing the sorbent. We are putting a new sorbents in with better quality in terms of carbon capture capacity, kinetics, lifetime. So this is how we are going to bring our costs down over the years. And I think that's really our really advantage. So this is designed for mass production. From the early days in the design, we really try to pay attention to the details of what can be mass production, go through mass production. And the other part was also it makes it easy for us to upgrade sorbents. There are specific decisions we made in our design early in the days to make sure when we want to have or Gen 2 sorbent, Gen 3 sorbent, Gen 4 sorbent over the years, it's make it easy to be swapped and always upgraded. So there are so many objectives that I think have been reached, or we are working on that in terms of corporate objectives, business objectives, technical, project, manufacturing. Just to name a few about the technical objectives. This is multi-reactor system integration. This is extremely important for us to minimize the use of the utilities and the balance of plant. There are a lot of custom hardware technology that we developed over the past 2 years, and we have IP around that. So this was the best opportunity for us to scale those up and try it out. The control and operation strategy is another part. As I mentioned, we have to be very, very efficient in terms of operation of this system. And another key important part is we are deploying a structured sorbent, and this has been our focus from day one that we started working on this, because deploying a structured sorbent, a sorbent that is not in the form of a bead or a powder, is critical, because otherwise you will be really limited in your efficiency of your system, how fast you can blow the air without blowing out all the particles, you know, how fast you can get the heat into the sorbent, how fast you can cool it. These are all achievable with using a sorbent that is structured, and that's been a major part of our efforts through collaboration and partnership, and scaling it up over the past 2 years has been a part of, you know, like part of our team's focus to work with our partners on that. So what you will see today, we will go through 4 steps. The first step is adsorption. That's where we get the CO2 out of the air. We move air at the speed through the fans will turn on, we will move the air, we will capture CO2 from the air, and we will show you the difference between the concentration of CO2 going into our machine and going out of the machine. The second part is we have an evacuation step. Basically, that's where we pull vacuum. There are multiple reasons. We want to make sure that, you know, our sorbent lifetime is very important for us. By pulling a vacuum, you reduce the chance of oxidation. Also, by pulling a vacuum, you will deliver a high purity CO2 that we will demonstrate. Then we will heat up our filters or sorbents, and by heating it up, it starts desorbing CO2. The CO2 starts coming off, and that's the fun part. And at the end, we want to get back to our initial step, and that means that we have to cool our sorbent down. And that's the last step we will demonstrate. This is the full cycle. After this is completed, you can go to an absorption step again, and you will see all the steps demonstrated right now.
Thank you, Saeb. Here we have a chance to show you what I find really exciting, which is some live data from our sensors on the machine that you all had a chance to take a look at. What we're starting now in just a few moments is the adsorption. And the way we measure how successful an adsorption is what's called a breakthrough curve. You will see the red line here is a CO2 concentration sensor that's at the inlet to our module, and the blue line is a CO2 concentration sensor that is at the outlet of a module. The difference between them is the amount of CO2 that's being removed from the machine when we're doing the adsorption. We're going to turn on the fans in just a moment now. Right now, these two sensors are reading the same because there isn't any air passing through our machine. But as we start them, and as the sensors take a second to update on our system. And there you go. The red line still represents atmospheric concentration of carbon dioxide, whereas the blue line represents quite a bit less. And the difference, obviously, is what we're capturing. I think adsorption typically takes quite a while. So rather than watch the entire set here, we'll watch these curves for just a minute while I think we take a few more questions.
Thank you, Brian.
Yeah, Brian or Saeb, I wonder if you could just more fundamentally speak to the challenge of directly removing carbon dioxide, which is a pretty trace element in the atmosphere, with a machine like this. I think that would be a good sort of baseline to kind of establish for people what the nature of the challenge is here.
Sure. So just to give you a little bit better context, like we always say CO2 is 420 ppm. What does it mean? So assume that 1 million molecules, balls, are flowing around. And out of that 1 million balls that are flowing around, there is only 400 of them that are red, CO2. We should catch them. So it's a challenge because you want to have a system that is very, very efficient, and you want to have also a material that is very efficient in picking up 400 molecules out of 1 million molecules, and that's amazing. And the second part is you have to design a system that is very efficient, because if we are talking about gigatons of CO2, just imagine 400 of these molecules at the time and how much they weight. So we have to move a lot of air through our system to process it and make it meaningful difference. So that means that the design of the whole system, the module, the way we are thinking about the placement of the fans, sorbents, especially structure sorbent, should be critical, because otherwise your pressure drop is going to be high. When the pressure drop is high, your cost of running the fans is high. So I think the kind of the challenge of removing CO2 from atmosphere is that you have to have a system that is very efficient in terms of energy moving the air, and the second is you have to have a filter in place that is very efficient, that look at 1 million molecule and say I need these 400 molecules out and take it out.
Yeah, and just to go a little bit more specifically into that, looking at it, it looks kind of like a beautiful piece of HVAC to a certain degree. Certain elements of it are familiar to us, but it's really that internal materials innovation is really the secret sauce of direct air capture. And Carbon Capture Inc. has a unique approach to that in terms of the development process, but the actual materials it's using. So I was wondering if you could tell us a little bit about what is the secret sauce of the CCI materials at the core of it.
Yeah, so I think from early days when we started looking into the cost of carbon capture, I think Brian has developed a very, very detailed techno-economic model. We are looking at the impact of different elements, how we can bring this cost down and meet our target at the end of the decade. And one thing that we just realized very quickly was the material, the filter that goes inside is going to be the key driver of the cost. So you need to always make sure that you are having something that is very efficient, but you have to increase the capacity, you have to increase the lifetime, you have to increase how fast it captures the CO2. Otherwise, if it's not fast in capturing the CO2 will pass by. So we started with a structure sorbent that is the state of the art, but we have a core team. Right now, Omid is our director of sorbent development team, and he has come with a lot of experience over the years from other carbon capture companies. So we have a core team that is specifically working on developing sorbents, but we have also embraced partnerships with many external parties, not only on the core sorbent development, but on the structuring, because there are many laboratories around the world, like hundreds of labs developing core materials, like grams of materials. Like, if this material is scalable, I don't think they know the answer. If this material is something you can structure at low pressure drop, I don't think there's a good answer for it. So we are really embracing the partnership. We have folks here even today helping us from large material companies that, I want to say Greg is here from BASF. So when we find the material, we can go to our partners and say, can you take a look at this material? Is this something scalable? Then we have our structuring partners. They come in and say, okay, this can be structured efficiently or not. So it's a full kind of process that we trying to control to make sure we get the best material to our machine as soon as possible. And our machine are designed in a way that is upgradable over time, that can accommodate the best sorbent and technology, and that's how we're going to bring the cost down over time.
Yeah, we're really just at the tip of the iceberg in terms of innovation around sorbent. So I think that approach to open innovation and collaboration is pretty unique, I think, within the context of DAC, and will serve you well. So we're watching this here. We're all riveted by what's happening here on the screen that's showing the adsorption. Everybody could tell us a little bit about what's happening here. How long is the adsorption process typically, and how do you know when it's done? What happens after that?
How it's done is a very good question. So first of all, what we are seeing right now, I don't know how, right now, how fast we are operating the fans. Is 90%, 50? Oh yeah, because of the noise, and we wanted to make sure you guys can hear me right now very well. We try to slow down the process a little bit, so we can control all of those parameters. One of the things in terms of when we stop, it's a very good question. It depends. Because you can, these filters are very efficient at the beginning in capturing CO2 because there is not much CO2 on them. So at the beginning they are very efficient, but when the time goes by, there are CO2 sitting on them, so they get a little bit slower.
Over the course of its life, you mean?
No,
yeah.
In the one cycle.
Oh, gotcha, okay.
So it's a question of when you want to stop. So you can go very, very long, completely saturated, and you can do it. You can have all the CO2 on the material and it's fully saturated, but it means that you have to run your fan for a longer time and you pay for the electrical energy. That doesn't look like a good idea. On the other hand, you can stop very quickly at a very high efficiency, but then go through your heating cycle. It means that you have to pay for your thermal energy. So at the end of the day is the optimization of energy where you want to stop. So we have developed detailed models and algorithms that can help us understand. Looking into breakthrough curve, depending on the temperature and the humidity, we can say the smart idea right now is to cut it when it is at 75% full or 50% full.
Gotcha. I think Brian's got some breaking news here, I think.
All right. As we mentioned earlier, we're going to switch to a different set of 4 reactors, one that we've already completed the adsorption process on, and we're going to go into the first step in the desorption stage. As you heard from Saeb, the first step in the desorption stage is to evacuate the reactors. Once they're saturated with CO2, we basically seal the space that they're all in. There's a lot of air left in the open space in between the space where our filters are. We want to get rid of that air for 2 main reasons. One, if that air is in that space as we desorb the CO2, it will mix with the CO2. And so by evacuating it first, we get much higher purity of our product, which is important for certain uses or sequestration. Second, unique to the materials in our reactor, to the class of sorbent materials that is the most common for direct air capture, oxygen at elevated temperatures can damage this sorbent. And so by pulling the air out before we heat up the material, we're also greatly extending the lifetime of these materials. Again, you see red and blue lines here. We've obfuscated some of the specific temperatures and pressures for our process, but still you can see that the blue line here is a measurement of the pressure in our reactor sets that we've just started the evacuation phase on. The red line is the temperature. So in this stage, because we're just pulling a dry evacuation with no heat or steam, the temperatures will remain constant, they'll remain at ambient, but you'll see the pressure drop quite a bit as we finish out this process.
Thank you, Brian.
Great. And I think there's a lot going on here. And again, just want to remind people there'll be opportunities to geek out on any aspect of what Brian and Saeb are talking about after the technical demonstration. But maybe it would be just look at this and the hardware and the software and the monitoring, how much iteration had to have happened to make this module work, to set you on a course for expansion. Can you tell us a little bit about some of the real learnings you had, or pivots or adjustments that were made along the way that maybe even surprised you as you were going?
So the adjustments were many. We have had daily adjustments, that's why I said I'm really proud of the team, because they already accepted that, okay, I'm going to go to work, there's going to be some adjustments, and we are fine, we're going to work through together. So in terms of when we were designing this, I think there was one time that we were very close to the production, and I was feeling that okay, some surprises happen, and I was feeling that, okay, this is going to be very impactful. So I tried to keep calm, and we got our mechanical, electrical team, manufacturing team together in terms of how we can change this design very quickly to make it work. And I was very, very surprised, and I can say I feel very proud that in 2 days they came up with a new design, tested, validated, and now we deploy it, because it was such an even better design, honestly, because we were so heads down from the first day. We didn't think through this probably. The second part is right now, over the past months that we have started deploying this, it's been a lot of learning. So we are very cautious about the data that we are presenting. Even many of our staff didn't see the data from P0 for the first 2 weeks, because we just didn't want to give wrong data to the people. So how you're going to place your sensors, and how you're going to read it from different sensors, and how you are going to interpret that data is critical. So this has been some of the very valuable learnings we have gained over the past, I would say, like a month of commissioning and getting it to this point, that how we can work and place different sensors and make sure the data that we are showing the people, the data we are showing our investors, public, are going to be something that we can put a lot of trust and be proud of.
Excellent. I think we have a transition.
So in short order, we've reached a sufficiently low pressure in our reactors. All the air is removed, and it is safe for us to now start putting in steam into the reactors to provide heat to the material. In this case, for this part of the process, the reactors remain sealed. So steam is filling into that evacuated space. As you can see, the pressure is starting to rise back up, but you also see, if we go back to the desorption chart here, you also see the red line here. It was the average temperature of the material in our reactors. So that's starting to creep up as well. We have a target pressure and temperature for desorption that we attempt to reach. And once we reach that process, we'll open up the outlet of our reactors and start collecting the CO2 that's beginning to be released.
Saeb, I think the mentioning of steam there as the heat source, and I think that is one of the kind of distinguishing factors in your technology. What are the benefits or reasons for using steam for the heat source for your DAC technology?
Yeah, so I think steam is a great source for both heating and cooling and also pushing the CO2 out. So why it's kind of we decided to go with this approach, when you use a steam, when a steam gets to your material, it starts condensing and basically it turns to liquid water. And that's the way, I think, from physics in high school, basically you start releasing latent heat. So the heat of steam, the heat that comes from steam is very efficient in bringing the temperature up. When we are done with that, and Brian, as he mentioned, he's going to open the valve, we have a lot of CO2 inside the reactor. We need to push this out in a very short time because we want to be efficient in terms of use of our utilities. So steam is also a good carrier that you can push the CO2 out, and is easy to condense out again because we have a condenser on the back, we condense the steam out and the CO2 just exits. The other part that the steam is cool is part of the cooling, is the last step that you will see, because you have basically water on your reactor. It's the other side of the process. When you start taking vacuum, that the steam starts to evaporate, and that's a very efficient mechanism for cooling your system back. I just want to emphasize that using a steam, direct steam, is not something that you can use if you don't have an efficient structure sorbent, as well as the utilities that designed for operating with that. As an example, you can use beads or, kind of powders, but because you have to contain them inside some area, then you have to look into heat exchangers that needs to go around it. And basically by using a heat exchanger, you are increasing your capacity, you are taking a space that could be otherwise allocated to carbon capture. And the third part is not very efficient, because then you have to extra metal and everything else in between that you have to heat up and cool down your system. So I think steam is a extremely friendly kind of source of energy for us.
But again, it sounds like unlocking the advantages of steam is sort of downstream of the engineering you did on the efficiency of your sorbent.
Exactly.
Is that right? Okay.
And then, the other thing is how efficiently you are going to distribute the steam within that system. It takes a lot of CFD and work that you have to do to make sure, you have this space. You want to make sure steam is going everywhere very efficiently and at low energy.
Gotcha. Great. All right, we're moving along here. Some other just questions that we have. What is the next phase that we're going to as well? Just a sneak preview in terms of what happens next.
So what happens next is when the temperature is high enough, then we open up the valve at the exit of the reactor. The steam is still coming, and the steam is going to push the CO2 out. The steam is going to condense, and the CO2 is going through our exit sensors, and you will see a reading of how much basically CO2 we are capturing in terms of the concentration.
Great. And just, here we are in beautiful Los Angeles, sort of a perfect day. We've talked about Wyoming. We've talked about Arizona as future places of deployment. How does it differ in terms of you evaluate performance across different types of physical environments?
Yeah, so I think direct air capture is a very interesting case for engineers. Because your environment is always changing. So basically, it's not like a point source capture where your feed up, gas feed is always constant. You can always predict what's coming to my plant. Here, we need to think about, okay, there is going to be day, night, high humidity, winter, summer. So we have to design a system that we can accommodate that. So in order for us to qualify and put some KPIs in our sorbent parameters and find our cycle parameters, basically what we do is we have really equipments that very strongly designed in our Los Angeles facility. We can test the material anywhere from negative 20 degrees C to plus 40 degrees C, and any humidity from 0% to 90% relative humidity. So by doing this test over there, we don't need to go to field. The field operation is going to be very helpful for us to gain real life experience, but we can predict from the machines that we have developed in the lab then how this sorbent is going to perform. And that's been very critical for us because we have a project in Wyoming. I think we are looking into other locations that are more hot and dry climates, so we need to have all of those knowledge basically gathered over time.
Excellent.
Okay, so we've just progressed to the second half of our steam heating part of the process. You can see with the pressure in the reactor measured by the blue line here, we've started to level off. Once we reach our target pressure for desorption, we control the rate of steam going into our system and the rate at which we're pulling gas out of our reactors to maintain those conditions for the rest of our desorption. You can see our sorbent temperature remains elevated. And at this point, the outlet of our reactors is open and CO2 is leaving our system. We have a measurement from our product at the end of our line here that is the purity of the gas that we are making. And as you can see, if we watch this for a minute or so, this will go up quite high. Some of the targets that we want to reach for our product, certainly 95% or higher, sometimes even a little bit higher than that, helps us be able to use our product gas for more sequestration with less conditioning after the process. I think we will all get to watch this plot for just a moment here and see just how high we can make it today.
Brian, just again, say that, just boil it down in a sentence exactly what is being indicated by that.
So this, as you can see on the y-axis here, is the percent CO2 purity in the gas that's leaving our module right now.
If I want to speak about the same like balls that I mentioned at the beginning, like you had 400 out of 1 million. So right now we will see how much we can get. But if we reach, for example, 90% purity, that means that 90% of molecules leaving the reactor is going to be CO2. So basically we got a very, very dilute, extremely dilute gas. We run it through our system and we get a very high concentrated CO2 at the outlet. And that's kind of what we're going to show here.
And Saeb, while we're watching that happen, could you just talk a little bit about the significance of CO2 purity in terms of what happens next to that CO2, how it's being utilized or stored?
Yeah, so I think for this machine right now, we are not utilizing this CO2 as a catch and release right now because we wanted to demonstrate the technology, also get a lot of learnings from this. But this is just the beginning. Next for us, we are working with some of our partners. I think I'll invite people to go to their tables and talk to them. We are going to utilize CO2 in concrete. And I think one of the people that have been, one of the teams that have been very active in this area, I think they have a table here, Cabin Built. I think 12 is another group that they have been working on basically taking the CO2 and use that to make synthetic fuel. So all of this kind of downstream products are going to be options that can utilize CO2, especially high purity CO2. But also we can use CO2 for sequestration, and the more pure CO2 we get out of our system, the less we have to spend for cleaning it up in the next step. So this has a direct impact on the overall cost of the capture for CO2.
Yep. It seems to have leveled off here.
So at this point, we've reached 95% purity of the CO2 coming out of our device. Typically, when we run this system, if we were to extend the steam desorption for a little bit longer, we would get up to about a peak of 99% on our sensors, which we're quite proud of. In a few moments here, once we've completed taking CO2 out of our device, the next step you will see is our cooling process. Again, we will show you the temperatures and the pressures in our reactor. In this case, we once again will pull the pressures in our reactor lower. This causes water, much like sweat coming off your skin, to be released from our material and will cool it down. This gets it into a safe temperature for the next adsorption cycle, where we can once again put air into our machines, once again take the CO2 out, and repeat the capture cycle over and over again. With that, this basically concludes the cycle that we're demonstrating, and I know we have a number of other people to talk about the device and the process, so I'll be handing it back over to Chris and Saeb.
Thanks, Brian. Yeah, I know that I'm conflicted here, but I want to tell you 95% purity is not a joke. So it's like getting CO2 from the air and making 95% purity has been like a big achievement for us.
Yeah, well, you might be conflicted, but somebody who's not is Matt Reisdorf, who's joining us from Florida today. And I think one of the things that's really impressive is, you know, we're talking through from an internal perspective about how the machine works, how it performs, but it's important to have other experts come and do that analysis separately as a third party and to be able to report back on that. So Matt, I was wondering if you could give us a little bit about what you discovered yesterday.
Sure, happy to talk. So we at Florida have been working with CCI for some of their future plans. As part of that, we've been able to look at both the plans and operate the facility that you see here today. And what I noticed in that facility might be what you noticed as well as you walked by. This is a very well instrumented facility. There are sensors to measure every bit of what goes in, what goes out, and how it operates in this facility. And those sensors are showing exactly what you see here, that the CO2 is being pulled out of the air, the CO2 is being concentrated, it's being released in a pipe that you can see outside right now, and being blown out, at this point being just blown out to the atmosphere, but by concentrating it's being concentrated into a spot that we can take that, compress it, put it either to use or put it into a place that's better to store than the atmosphere. And I congratulate CCI for everything you've done here today. I also appreciate that we're not done, and we look forward to watching CCI and helping CCI grow to build more, larger, and better facilities to keep doing what we're trying to do here today.
Great, thank you so much. Great.
Thank you very much, Matt.
Great. So you've heard the team show and demonstrate that this is awesome. You've heard Matt as a third party say, yes, it is in fact awesome. But what I'd like to do is the other part that I think is really impressive is the commitment to innovation on the manufacturing side here in the United States. So for that, I'd like to bring David Afson, who's the VP of Manufacturing at Carbon Capture. And
bit of a karaoke fan if you got any Sinatra requests.
Let's do it. Tell us a little bit about, again, there is a unique approach to sort of open design that facilitates iteration and change, which is critically important in a space like direct air capture. So tell us a little bit about what's special about the vision for manufacturing here at Carbon Capture.
Well, I think the one challenge you've got to consider in manufacturing is typically when you think about building a product at scale, you think about building the same product day in and day out, right? Adrian had mentioned my experience at Tesla. We wouldn't build the same product. Yeah, it was the same car, but it had different parts, right? So the important thing you've got to consider, that's a first of a kind. I'm not going to be building that next year. It's going to evolve, right? We need to have a process in manufacturing to be able to accommodate all those different changes that we need to be able to make. And what's really important, and again, from an automotive perspective, you need to actually test and validate the thing before you send it out the door. We'll do that same thing in the manufacturing facility, establishing testing and validation equipment and criteria so that we can actually confirm that changes we make in the manufacturing process are actually what we wanted to intend before we get the product out the door.
Gotcha. And one of the key metrics that we have for the success and takeoff of direct air capture is obviously improving costs to really bring the cost down and to increase the efficiency. So I'm wondering from a manufacturing perspective, what's on the immediate horizon in terms of the greatest opportunities for cutting costs and increasing material efficiency?
So the short term, and we've already started into procurement for the next phase, and we've diversified our supplier base about 400%. Actually, we've gone out and gotten different quotes and are starting to get more competitive cost action on the components that we need to procure to build the subsequent product. The second thing is the adage goes, volume forgives all sins in the cost department. So obviously as we scale, we're able to be a lot more cost effective, but just sheer number of production components we need to build.
Excellent. Great. Is there anything else you'd like to add about the, I guess what you could say, sort of designing products for manufacturing? I know there's a lot there, but I didn't know if there was anything else that you wanted to add.
Well, so, the principle of modularity in this product is our foundational strategy, right? And honestly, it's a great product, right? But, think about this unit's 500 tons. You watch that video, 10 billion is the number we need to get to by 2050. That is 20 million of those units, right? As a car guy, I'm used to high volume of scale. There have been 3 cars in the world that have hit that volume in the history of mankind, as an example, right? So, example specifically, the world has produced 21 million Volkswagen Beetles in human history. So,
Yeah.
that's the scale, right? Now, if you think about it specifically in terms of the components and the parts, what you got to do first is actually simplify this very good design into what is manageable, because the number of parts is really going to impact your logistics, your ordering, your manufacturing processes. We're probably north of 1,000 individual parts in this unit. I need to cut that in half as a start, right? And then the second thing is, and a lot of that can come through commonization. Think about bolts, fasteners. Use them as much as you can repeatably, right? And then finally, the parts themselves, as far as tolerancing, it's not about having more accurate parts. It's about having the tolerance of the parts that you really need in order to be able to execute simplified assembly.
Yeah, and it just seems that as a guy who came out of solar and batteries, the modularity is the gift that keeps on giving in terms of learning rates and discovery and being able to make tweaks as you go along to reduce costs and make the product better. So the formula is a proven one, and it's really impressive to see it applied here for direct air capture. So thanks so much, David. Really
Great.
appreciate it.
Let's get to work.
Yep, let's do it. Excellent. Well done. I'll get this back here. So we're just going to close off again, and to emphasize the importance of that, as we said, secret sauce, the sorbent, to be able to come up with innovative new forms of sorbent is one thing, but to develop a supply chain where you can actually match that innovation to the need of scale that we have. Can you just tell us a little bit as a close about what are we looking at about being able to develop an adequate supply chain for sorbents to track with your growth?
Yeah. So good question. One thing is at carbon capturing, one area that we wanted to make sure in every aspect is making sure the perfect doesn't be the enemy of good. Okay, so we do have good sorbents at this point that can be scalable and are available, and we are deploying in our machine. But that's just the beginning. Like, we can't use the same sorbent 2 years or 3 years from now. So that's why we have developed a roadmap of minimum of 4 generations of the sorbent over the years. And, Gen 1 is already deployed. We are working in terms of improving all of these metrics. But what is the critical is bringing the other partners and the partnerships that we are making early in the process to get their feedback. And we are actively involved with many national labs, universities, research labs. Like we are actively working with external people, and honestly, we are not hiding it. We are very proud of it. So we want to make sure when people have a new material, there is a pathway for that to get deployed into machine, and there is a pathway for us to get our costs down. And this is CCI as a startup company based in Los Angeles. We are not going to have the bandwidth to do this. So we are heavily relying on our partners, and we have had great partnerships so far that helped us a lot over the past 2 years scale up to this scale. And honestly, there is no barrier for us to scale up even more. But we want to make sure we are always working with the partners from the universities, from material companies, from structuring companies, and we bring all of this together to make sure that we end up with a product that can work for direct air capture at low energy, low environmental cost, and bring at the end of the day the cost of the carbon to what we need by the end of the decade.
Great. Well, that concludes our technical portion here. And let's give a big round of applause for Saeb and his technical team for what they've managed to do here. This is a historic day, certainly for Carbon Capture Inc., but for direct air capture as well. A lot of people have a lot of questions, I would imagine, about different things that we put together in this last 40 minutes. Saeb, I think you have a few people that you think could be point person to answer people's questions as we go into lunch and after. Did you want to have them raise their hands, or did you want to name them?
Yeah, sure.
Yeah.
Before that, I think Brian has an interesting show and tell. This is how much
look at
CO2 we captured.
Ah, look at that.
So if we want to know, like we wanted to show, like, based on while we are talking, running this cycle.
I don't know if I could do it. I will not impress you if I can't lift that.
So, or reactors that can remove about 50 pounds of carbon per cycle. And we have been running a cycle in front of you, and you can imagine how much molecule of CO2 you need to remove to weight that much. So that's one part we wanted to say. In terms of your question, we want to make sure we answer your question to the extent that we can.